introduce the environment, introduce the interference. Okay, so then to deal with this cumulative this error, okay, frequency hopping error, then we get a derivative of this phase difference again. Okay, then after differentiating the phase difference signal, then we'll only have this estimation error in the first example when the system jumped to a new channel. Okay, but for the following examples, 2, 3, and on the same channel, such a cumulative frequency hopping error will cancel each other. So then we just drop the first example, then we can make the remaining examples will all be useful. Okay, so that after this operation, then we get a signal. Okay, a derivative of the raw phase difference signal like this is plotted in this figure. Unfortunately, okay, so we clearly we have removed the cumulative error, but unfortunately this signal is very random. It's still very random. It's not useful. The reason, yeah, is that so as shown in this figure, so this is the phase difference signal in the frequency domain. So we can see there's a peak here. So that corresponding to the human activity. Okay, so but when we get the derivative of the phase difference, so the differentiation operation is actually equivalent to a convolution with a vector of f and minus f. So this is in the frequency domain, this corresponding to a high pass filter. So basically, we are filtering out, by doing this, we filter out all the useful information in this hidden in this spike close to 0 Hertz frequency. That's why we get something like this. Okay, so then once we know the reason, okay, the cause, then the solution becomes easy, simple. So basically we just apply a low pass filter. Okay, so before we differentiate the phase difference signal, so we can suppress the high frequency noises, and so then this help us to retain the low frequency information that we're trying to get from the RFID signal. Okay, so in this example, for the same 30-second period, okay, so you can see after this operation, differentiation, no, first the low pass filtering, then differentiation, then we can see very clear spikes that corresponding to the nodding of the head. Okay, so now this signal is very useful. Okay, becomes very useful. Okay, so the next challenge is suppose so many RFID applications are indoors. So we have a very clean stationary environment, controlling environment. So it works well. But suppose we are trying we're trying to apply these systems, such systems, in a dynamic environment, like a driving environment in cars. How about using RFID tags to measure the respiration signal of the driver? Okay, so that can be an indicator of the driver's like a condition. Okay, if the respiration signal gets slowed down, very smooth and slow down, that means the driver is tired and is close to sleeping. Okay. Then in such dynamic environment, then there's a challenge from the environment. Okay, so for example, the vehicle is vibrating. Even if you're not the car is not moving, but the engine is on, so the vehicle is always vibrating. And when it's when you drive through in the streets, okay, so then the road is not flat. There's a bumping. Okay, and also we will turn the driver, okay, will not be stationary quiet all the time. The driver will turn the wheel and look around for traffic, and there will be also passengers around. And all these movements, okay, in the environment will generate a huge, strong interference to the RFID signal, because the tag will be is moving. Okay, because due to this move, such interference. Okay. So for in recent work, we use RFID tags, a pair of RFID tags to detect the nodding, okay, of the driver, nodding movement of the driver. So usually when we drive alone and when we're tired, so basically you keep on nodding your head. So that is an indicator of a fatigue, okay, driver fatigue. So yeah, so then how do we deal with this kind of interference from the environment? So the idea is to use a very easy, okay, use a kind of tag deployment. Okay, so we put two tags, okay, parallel, okay, horizontally parallel on hat, and the driver wears the hat, and the reader is put at the back of the driving seat. Okay, so if the driver is looking around, okay, for checking the next lane for traffic, for example, okay, so then these two tags, the movements of the two tags relative to the antenna will be similar. So when the head turns, then both tags will move in the same direction. So if we use a phase difference, the difference of the phases read from these two tags, then we can cancel such interference. Okay, so yeah, then but if the driver is nodding, then usually one tag moves away from the reader and the other tag moves closer to the reader. Okay, so if you check the phase difference, then it will be different. So that is shown in these two figures. So in these two intervals, okay, in this interval and this interval, the driver is rotating his head, checking traffic. Okay, so and during in the middle, okay, so from like 10 seconds to 20 seconds, the driver is nodding his head. So from this figure, we plot the phase read from a single tag. So from this phase information, we cannot distinguish these two kinds of activities, movements. But if we use the difference of the phase read from these two tags, the phase difference, okay, so then we can see for the nodding period, then we can see there are 4 peaks, okay, very clear peaks. And for the head rotating interval, then we don't see those peaks, okay. And similarly, the body movements of the driver and also interference movements caused by passengers in the same car can be mitigated in a similar manner. Okay, and then the next challenge is that the signals we are interested in is usually they are very tiny signals. For example, like the chest movement when we breathe. Okay, our chest moves slightly, and this such useful information, such useful signal are usually buried in very strong noise. Okay, and other useless signals. So how do we extract such very small signal, useful signal from strong noise, the mixed signal? Okay, so one technique we tried, which has been quite effective, is called is a tensor decomposition. Okay, it's called tensor decomposition. So the idea is that as you can see here, all the information, the phase information we read from text, phase difference or differentiated phase difference, they are one-dimensional data. It's the time series data, right? So then we can, from this one-dimensional time series, we can apply a technique called Hankelization to construct a Hankel matrix that become to make them two-dimensional. Okay, that matrix. Then with multiple matrix, like we can use the matrix collected from different antennas, from different tags. Okay, if you have multiple tags deployed, then eventually we can construct a tensor. Okay, in our work we constructed all the 3 tensors. So that is a matrix, but it's a 3 dimension. Okay, so it has a three dimensions, all the 3. Then we apply tensor decomposition to decompose these all the 3 tensors into the summation of the inner products of vectors. Okay, so in this example, we decompose this tensor into m components. Each component consists of 3 vectors. Okay, then these vectors are the useful information that carry the that carries the human respiration signal. Okay, very small signals. So one question is how to determine this m. Okay, so how many components you want to decompose. So we showed that if in the ideal case, if we only have, there's no noise, no interference. If we only have this chest movement, let's model that by as a sinusoidal wave. Okay, sinusoidal wave. Then we can decompose the Hankel matrix into 2 components, and each one has exactly the same frequency or same frequency as the original sinusoidal wave. Okay, but in the real world, then we will always have interference and the noises. So then we can decompose this tensor into 4 components. Okay, 2 of them, as this example shows, 2 of them represent the human respiration signal, and the other 2 are the represents all the interference from the environment. Okay, then after tensor decomposition, it's a technique called CPD. Then we can obtain these 2 signals. By fusing these 2 signals, eventually we get a very smooth, very nice signal. This is the respiration signal we extract from by analyzing the RFID data. Okay, so then once you get this signal, you can estimate the respiration rate. Okay, so from the signal itself, we can also learn a lot of information about the health condition of the subject. Okay, so another challenge is the RFID data itself is highly sparse. So suppose in many cases we are not, one tag may not be that useful. We need to deploy multiple tags. Okay, that the previous example shows we can put the 3 tags on the chest, okay, of the subject. So then suppose now we have a tag array, okay, multiple tags deployed, and they are interrogated by this antenna. Okay, so because the original design of this RFID tag system is that we should always avoid collision. Okay, so otherwise, if 2 tags simultaneously transmit their response to the reader, then these 2 signals will interfere with each other, and so none of them could be decoded, right? So RFID system always use like a slotted aloha-like or binary tree search-based kind of sampling approach to avoid collision. So then the consequence of this protocol is that suppose we have an array of tags, n tags. So every time, so this horizontal dimension is time. So every time we can read only one. We can read from only one tag in the array. So in this time slot, we read a message response from the first tag. Then we can extract the phase data from this first tag. The next time slot, we get a response from the second tag, and so on. So after a certain time, then the system jump to a new channel. Then we get a response from the second tag, and so forth. Sometimes if the query could fail, so that means we don't have any valid phase examples, okay, for that time slot. So if we write these examples in such a matrix form, the x direction is the time slots, and the Y direction is the tag ID, first, the second, and so forth. Then we get a matrix that is very sparse. So for each column, we get at most one example. Sometimes we don't have any examples in that column. Okay, so this is a very sparse signal, and so how do we? So and we need to do like perform real-time sensing using this very sparse signal. So that is a big challenge. Okay, so what we tried, a technique we tried is this tensor completion. It's called high accuracy, low rank tensor completion. Okay, so similarly, we first transform those like data, RFID data, organize this data in the forms of all the three tensor. Okay, so then we apply this tensor completion technique. So in this tensor, okay, so it's very sparse. So we have some valid examples, but many other places is empty. Okay, so as shown in this figure, so we have these diamonds, okay, blue diamonds. Those are the valid values. Okay, and the purple line is the ground truth. So we keep on measuring those values. So the purple line is ground truth, but what is available, only these blue diamonds values are available. Okay, so then we apply the matrix completion. So the green line is the result. So this gives us the accurate estimations at this ground truth, these blue diamond positions. But other than these positions, you can see there's a lot of zeros. So the green line is very different from the ground truth, this purple line here. Then this red line is what we obtained using this tensor completion. So you can see there's still difference here. So there's a big value here, but in the ground truth, we don't have that value, right? But in most cases, you can see the red line is recovered from the sparse tensor from these blue diamond values. So it matches the purple ground truth very well. Okay, so this tensor completion is a very powerful tool we can use. So eventually, once we get all the data, okay, the calibrated or cleansed RFID data, then we want to analyze those data to detect useful information. Then from this aspect, machine learning, there's a lot of useful tools from the field of machine learning. So we can borrow, we can replicate, we can apply to our problems. Okay, so many techniques have been proven effective in like computer vision, natural language processing, but we can apply them to analyze the RFID data. But there's a accuracy concern issue, right? So most of the sensing applications are real time. So we need the model to operate very well, execute very fast, and complexity. And another challenge is how to get a sufficient large amount of labeled training data to train your machine learning models. Okay, so those are the several challenges, and we met, and the lessons we learned actually when we were working on such problems in the past field. So in the next few slides, I will present several applications we have tackled. Okay, so the first one is respiration monitoring, okay, and apnea detection. So apnea is a very common kind of sleeping related disease. Okay, so many people actually have it, but probably you don't know. So it is like showing these two curves. So in the upper curve, so the subject will breathe irregularly, then stop breathing. Okay, then after a while, after some time, then start to breathe again irregularly. Or in some other cases, you could breathe very smoothly, then suddenly stop breathing. Okay, so this it's very hard to detect the apnea. Okay, so because it's hard to in our homes, we don't have the technology or a device to monitor our respiration rate, right? So it would be very inconvenient and costly if you go to a hospital, sleep there for a few nights, then with all the sensors hook up to your chest and the brain, then your head. So that would be very inconvenient, right? So people have developed very interesting systems in prior work. Okay, using it's a contact-free and non-intrusive wireless technology. Okay, so there are radar-based systems like a UWB radar and FMCW radar can be used to detect the respiration of the patient, and then Wi-Fi-based system, including some of our work. Okay, Fitbit, Respit, and TensorBit, and with the TensorBit, we can detect multiple persons' respiration rate in a controlled environment. And there are also there was a RFID based system called TechBreathe. That's yeah. The RFID based system was presented in I think it's ICT-CS 2017 paper. So, but it only uses one tag, and it doesn't consider like frequency hopping and IP-near detection. So this is what we tried. So we developed this system called auto tag. Okay, so it put text, we put text on the chest of the patient, then use the antenna to read from the text to detect the face angle. Then we calculate the phase difference and calibrate the data. I think we have discussed all these components before. Okay, then eventually we got the clean respiration signal by analyzing the RFID phase data. Then we apply a machine learning, deep learning model, okay, to analyze the data. It's more like an anomaly detection, okay, to detect the anomaly respiration patterns. Okay, so that's the machine learning model is given here. So it is actually a autoencoder. So we LSTM, long short-term memory-based autoencoder. So the input signal is to recover the respiration signal from RFID data. Then first, this is compressed to the these samples latent variables z and its variance and its mean. Then the decoder will reconstruct the signal using this information, latent information. Okay, so then we compare the output, the reconstruct signal, and the input signal. Okay, if they are very similar, so the idea is so IP-near signals, IP-near data is very hard to obtain, but the regular breathing signals are very easy to obtain. So we train this model, this autoencoded model, using regular breathing signal. Okay, so the consequence is that if the input is a regular breathing signal, then the output will be look like a regular breathing signal, and these two signals, the input output, will be very similar to each other. However, if the input signal is an IP-near signal, okay, so then output will be very different because the autoencoder is trained with a regular normal breathing signal. Okay, so then we just compare the output signal and the input signal as indicated by the KL divergence between these two signals. Then if it is very large, okay, greater than threshold, then we think it is IP-near. Okay, the input signal is an IP-near signal. Otherwise, it's normal respiration.
Sorry to interrupt. 5 minutes.
Okay, yeah, I'll be quick. So we implement the system using off-the-shelf RFID tags and readers. Okay, so that's my student Chao Yang. He's testing his breathing. So as you can see, the results, okay, are very accurate. So the median error, okay, in these two laboratory and corridor case, okay, the median error is like less than 0.1 breath per minute. The maximum error is about 3.4, okay, breaths per minute. Then later on, we move the system into a driving environment, okay, in a car. So we mount the antenna above the driver's seat. Okay, then we put the tags on the tag on the belt. Okay, then the antenna will interrogate these tags, and then eventually we'll analyze the RFID signal. Then we can detect the breathing signal of the driver. And so as we discussed before, in such driving systems, then there's a lot of vibrations, interference from the environment. The driver himself or herself will also keep always moving, right? You need to turn the wheel and check for traffic, for example. So that causes a lot of interference. So apply this CPD, tensor completion, tensor decomposition technique. Then we are able to recover the very small, this is a system, okay. We can recover the very small respiration signal of the driver from the RFID signal. So this is the antenna. We have 3 tags mounted on the seat belt, okay. So the laptop computer and the radar are put on the passenger seat, okay. So we tested the system in several different conditions. So one is the car is parked at a parking lot. The engine's on, but it's not moving. Then we try the highway driving and the in-town driving. So these 3 curves are the corresponding distribution, cumulative distribution function of error, okay, of the respiration rate error, estimation error. So you can see the system has been quite accurate in all these 3 cases. Okay, in-town driving is the most challenging case because there's a lot of traffic stops, and you check for traffic and turn at the corner of the you know. So yeah, I'm sorry. Yeah, my laptop is battery is low. Just give me a second. Okay, so you can see, but overall, we also tried a different number of passengers in the car. So overall, this technique is quite accurate. Okay, so the next piece of work we tried is, I think we discussed this. So we want to detect the nodding movement of the driver. So that is indicative of his like his sleepy or his fatigued state. Okay, so we put the 2 tags. Okay, we put a reader at the back of the driver's seat and 2 tags horizontally on the back of a hat, and the driver is wearing that hat. Okay, so then we also use autoencoder, okay, to analyze cleanse the RFID data. So eventually we can we also test the system in the real driving environment. So you can see the errors, the accuracy are within like a 80–90% range. Okay, so it's quite, or in like when the car is parked, it's on highway driving or in street driving. Okay. The last piece of work I just want to briefly introduce is on this human skeleton reconstruction. So this is an important topic in human-computer interaction or video gaming authentication. Okay, so basically we capture the skeleton, okay, of this human. Okay, then that construct. This is like a regression problem. Okay, so we can use the skeleton for authentication, for gaming, for many other applications. But the video camera-based approach has been very successful, but it also brings a lot of privacy concerns. Okay, so people don't feel comfortable if you have a video camera is watching at you all the time, right? So there are also like a Wi-Fi reader and RFID-based techniques. So we in our work we have we put the RFID tags as a wearable sensors. Okay, 12 tags attached to the body. This is my student Chao Yang. and we have 3 antennas, okay, to cover this text, okay. So, and then we use video data. We use a Kinect, okay, data. So this Kinect data will provide us with the labeled data for supervised training. Okay, so we'll train our machine learning model is a deep kinematic model using this video data. But in the real operation phase, we don't need the video data. There's no privacy issues. Okay, so. And the challenge again is that this is a yield post problem because it's a regression problem. We need to reconstruct a video. Okay, it's a video. Okay, so the video is a skeleton moving over time, but it's a continuous video sequence. Okay, but the RFID data itself is very sparse. Okay, so it doesn't provide much information to reconstruct a video of human skeleton. Okay, however, we applied those kind of data imputation techniques. Eventually, we made it work. Okay, so here is
sorry, sorry to interrupt. I think we are running out of time. So can you speed up a little bit, please?
Yeah, I'm one slide away. Yeah, so here is the video we captured. The blue skeleton was the ground truth captured by the Kinect, and the red skeleton was reconstructed from the RFID data. So we also have the results for different type activities. Okay, so different movements like twisting the body, or yeah. So the accuracy, the median error is about 2 or 3 centimeters. So in conclusion, we presented our work, several applications on applying RFID sensing, okay, as a wearable sensor to detect human activity and human vital signs. Okay, they are built with real commodity RFID devices and evaluated in real-world scenarios with good performance demonstrated. And this is a multidisciplinary area. So you can see there are a lot of techniques, wireless communications, hardware device, signal processing, machine learning, healthcare. Okay, so and machine learning plays a very important role here. And yeah, as we are gaining more and more understanding of wireless communications, so wireless applications, I feel it's now becoming a very important playground. Yeah, and a lot of interesting problems to be solved. Yeah, thank you. That's all I have.
Okay, thank you very much, Professor Mao. This is a very interesting topic. Actually, we have some questions in the chat, and I already forwarded some of the questions to you through the private chat. But first, let's check. Krishna, are you still there? Do you still have a question to ask? You can unmute yourself if you do. Krishna? Okay, then we can move to the next question.
Yeah, I think I read the question. So basically, we just choose a reference channel. Then we don't care which channel will be the next, but we do estimate the phase offset between the current and the next channel, and then translate the phase samples collected from next channel to the reference to that based on the reference channel. So yeah. Okay.
Okay, Krishna, hope that answers your question. Our next question is from Chen Wan. So the person said this is an excellent speech. He had some questions. First, are all simulations based on practical data measured in humans? And the second question is, are there implantable medical applications based on RFID technologies? how deep can those tags be implanted in the human body? Also, if the tags, if the tag is implanted in a human body, since the implantable tag will exist in the human body for a long time, is there any radiation considerations?
Yeah, these are very good questions. For the first part, we it's not a simulation. So we really build all the four systems are implemented with commodity RFID readers and tags. So all the results are from real. We also in challenging like real driving environment. So those are real results, and yeah, so it's not a simulation. And I have no idea about these implantable devices because we are not. I think there will be more strict like IRB like or regulation about if you want to do experiment like that way. So we haven't tried that, but yeah, I'm not sure about the radiation or risk. But I think because FCC has a very strict regulations, safety requirements of for the radio devices. Okay, so I don't think there will be a lot of risk on radiation on human on the subject. Yeah.
Okay. Um, in addition to these questions, I actually have a few questions to ask.
Okay.
First of all, I noticed that, so we're using RFID, so I assume that the power consumption is pretty low. But when you show us the experiment settings, I do see some NVIDIA graphics card, which are, I think, power hungry.
Yeah.
Or also right now it's difficult to get them. Anyway, so my question is, what's the overall system energy consumption? How long those tags can last?
The tags they are passive tags, so they can last forever. So basically, they don't. There's no. Yeah, there are like tags with a battery, with embedded battery on the market. You can make use of. So that gives you a larger range, longer range. You can operate them. But the tags we use are just a commodity off-the-shelf passive tags, UHF tags. So they don't use any battery, so they can last forever. The reader is connected with a power supply, so the reader
Mm.
will transmit a signal to the tag. Then the tag will resonate and then generate a little power based on the incident signal, and then return return a response. But it's not powered by battery.
Okay, thank you. My next question is actually related to, do you know that recently there's a computer game called Cyberpunk 2077?
Mhm.
Of course, I won't tell my student that I know that game. I just pretend I never heard of that. But that describe a world in the future that you have the human body has tons of implants. You have your the augmented parts, like artificial parts in your body. And in that game, there's a common technique that if you want to attack somewhere, you can hack into the body, into the human body, disable some parts of those of the enemies. So that brings a question about security. How if in the future we have all more of this kind of implant, do we need to worry about the security, or how do we? I think a better question is how do we uh, improve the security of that such a system?
Yeah, it's a very good question. So we haven't tried the security problems yet, but I think it's a very important problem. As you said, people can hack into your wearable device or implant device and make trouble to you. And also, what we consider the privacy issues. So basically, my heart rate, my respiration signal are my privacy, right? So I don't want anyone standing outside my window, they can collect such information from my body. So, but we haven't got some good results yet. So ideally, you want to introduce some like artificial interference to the in the system. So because you know the interference, you can cancel it. But a eavesdropper probably will not be able to get rid of the introduce the interference. That's the idea. But we haven't we don't have any good results yet. Yeah.
Okay, great. So is there any other questions from the audience?
I think
You can unmute feel free to unmute yourself and ask a question.
yeah, I think there's a question from Stephen Walk about the issue. Is there any issue because of delay? So we uh, so as you can see, these applications they are kind of real time, right? So we measure the person on, right on the time, but they are not that real time. So basically, respiration, if it's 1 second or 500 milliseconds late, we detect the respiration rate like 200 milliseconds late. So I think that's tolerable. So we haven't really considered the impact of delay yet. So many applications um, like a sleep monitoring. So you monitor the patient uh, over a night, 8 hours sleep. Then so basically for such applications, delay is not an issue at all. But for driving applications, so that may be critical. So maybe 200 milliseconds then will make a big difference. But uh, so basically, our idea is that we measure respiration, we measure the head nodding. So this is like a warning signal. So like we can transmit some a beep or some noise to wake up the driver. But it's not like uh, we don't expect that we can immediately when the accident happens, then we can immediately detect it and alarm the driver. So
Okay. So any other questions?
there's a question about the 900 megahertz band is the same as the Wi-Fi band.
True.
So therefore, radiation constants should be the same as that for Wi-Fi. But this, because we use commodity RFID devices, so it's all follow the FCC requirements. So, and it's the so we don't we never see any problem with the like interference with Wi-Fi or we are interfering with Wi-Fi. So, and these are near field communication technologies. So its range is like 1 yard around the patient, the subject body. So I think the interference issue is not comparing to Wi-Fi. Okay, so there are also Wi-Fi based techniques. Okay, to for example, we have Wi-Fi techniques to detect the heart rate and respiration, and it works so even like across the wall. But those Wi-Fi signals has a much larger range. So if you the signal will be very sensitive to movements. Okay, so somebody is moving next door, then that will introduce interference to your heart very tiny heartbeat signal. So that's a shortcoming or a limit of like Wi-Fi based systems. Yeah.
Okay. Professor Mao, there's a question from Chen Wang. The person said, I noticed that ultrasound is mentioned in a slide. How to use ultrasound with RFID?
Oh, we basically ultrasound is that we mean that there are ultrasound based solutions for like for example respiration monitoring. I don't know any like RFID tags we work with like that work with ultrasound. Yeah, we have a work. We basically we wrote a smartphone app, so that can turn your smartphone into like a yeah. So basically, we use the speaker of the smartphone app to make it transmit ultrasound at 20 kilohertz ultrasound, then the signal will hit on your chest and then pick up by the microphone of the smartphone. Then we can use this to detect the respiration rate. It works very well within like a 1 yard range. Yeah, but it's not that is not RFID based solution. Yeah.
Okay, thank you. Another question is from Ashok. Are the sensors mounted on the body? If so, do clothes interfere with the measurement?
Yes. So let me show you. Yeah, let me show you a photo. Just give me a second. So the sensors, the tags are used as wearable sensors. Okay, attached to the human body. Yeah, but I don't know why. Just give me a second. Yeah. Go back. It's like this. So we put the RFID tags on the body. It's not on really, but it's on the clothes. So with different kind of clothes, we tried. For example, for respiration rate monitoring, we tried the um, different clothes. For the ultrasound-based system, we tested our smartphone app with different kind of blankets, for example, so that they do have an impact on the accuracy. So the ideal case is that you don't wear too thick clothes that are too thick. Okay, that will be will reduce the signal strength. I mean the chest movement. That's our signal. Okay.
Okay, then the final question is, what are some of our future applications in the pipeline?
Let me see. Yeah, we are thinking about this. Yeah, so yeah, we have work on skeleton, for example, because it's we publish papers, right? We implement the system, we design the system, implement the system, test it, and publish paper. But I think there's a still big gap between a real product everybody can use. So how to make the system more robust, right? So that is a big issue. And maybe you want to use multimodal data, because one kind of data will always have its limitations. It works there's some always corner cases that doesn't work well. But if you use multimodal data, then they will complement each other and give you robust results. So for the humans 3D human skeleton estimation work, we're working on the generalization of the model. So there are two problems we are working on. One is that when you train the system, the deep learning model, with one setting, okay, one kind of placement of the antennas, and one subject, can you transfer this trend model to apply it to a different subject, maybe a taller patient, or maybe the antenna placement are misplaced, are indifferent. So for wireless signals, if the antenna is misplaced for half a wavelength, then you may get very different results, right? So we tried meta learning. So there's a machine learning technique called meta learning, and few shot fine tuning, and that works very well. So we try different positions in front of my student Chow. He has 12 tags on body, but he stands at different positions relevant to the antennas, okay, or a completely different environment. So we showed that meta learning works. So you can train the model in one environment, but you can apply it to a different environment. It still give you good results. And another potential problem is that so how do you we were considering data augmentation. So deep learning models requires a lot of data, high quality data, labeled data. So to train, you use data for supervised training to train deep learning model. So in our system, we use the Kinect video camera capture the data, then use that as a label data training system. So how can we make it easier? So if we has less dependent on data, then the system can be easily deployed in different environments. So you don't need a lot of training, right? So like you use Siri, then you need to read a few sentences. Then Siri will learn from your accent, your voice. Okay, then you can handle your future. So it's similar. If we can minimize this dependent on training, so that would be great. Yeah.
Okay, great. Although I said the final question, but then in the chat, Tim posted a very interesting message. Tim mentioned that the Google Home and the Amazon Echoes, the smart appliance or the smart speaker everybody has right now, it is so sensitive, so it can actually detect someone's respiration and possibly the heart rate. So you can use that to detect heart attack. That's very interesting. And I also read an article talking about, actually a paper talking about using laser pointing at someone's Google Home or Amazon Echoes. And then you can use that to hijack another people's home, to unlock your smart, to control your smart device from outside of your house. So that poses some serious security threats. And those are also interesting things to explore.
Yeah, there are people working on acoustic using those smart speakers, yeah, to for like intuition detection or authentication or vital sign monitoring. We are currently, some students of ours are working on project. So basically, we use a microphone array. So it's not just a single speaker, but it's a microphone, but it's multiple. They form a array, then they give you very good results. But we don't have a paper yet. We are working on paper right now. So yeah, that's a very good idea.
Yeah, and also from Ben Mayer, um, the question is, for distance measurements from each sensor, how is the region determined?
Yeah, so we basically we detect because we are interested in detecting the activity and the motion, like movements of the chest. So basically, we are interested in the variation in the distance, not the distance itself. But if you are interested in measuring the distance, then there's a lot of a huge body of papers of work, so they can give you. We not a couple of years ago we used the antenna, use it as a sparse antenna. No, we use the RFID tags, but put them at irregular positions. It's like a sparse tag array, and we use this as a antenna array. Then that give you very good estimation of distance. So there are a lot of papers on measuring, locating a tag. Okay, distance measurement.
All right, I think we're already run over time. So first of all, thank you, Professor Mao, for this very exciting and informational session. And also a big thank you goes to all the participating ComSoc chapters. And most importantly, like I said last time, thank you all for coming to attending this event. Oh, by the way, this time we have co-host from India. And recently we heard a lot from in the news. Hope the situation in India can get under control very soon. And to the friends, have colleagues from India, our hearts are with you, and our prayers are with you too. So we're in the pandemic together, and let's fight it together. And so please take care and stay safe. I think we'll beat this virus together and get through this difficult time, and we'll become stronger than ever at the end of the tunnel. So again, thank you everyone. And as a reminder, we have set up an online survey. So your input will be very, very helpful. And again, thank you everyone for coming. That's it for today. And I'll see you in our next event. Thank you
Thank you.
and bye.
Take care.
Take care.
Stay safe.